Okay, so we're there at the final question of the SAMS Paper 2 higher tier Edexcel physics paper. This is a really, really hard question, and I use this, the later part, with my year 13 students when they're learning about a similar, well, the same topic, and they find it okay then. Okay, not super easy. So it's a very, very hard question, and I've not seen it come up in such a hard way in the real exams here. Remember, this is a sample assessment. The start's not as terrible. Okay, so question 10. The espresso machine shown in figure 27 is an electrical appliance. The espresso machine has an electrical heater connected to a 440 volt main supply. The power of the heater is 3.5 kilowatts. The rating of a fuse is the current above which it melts. Which of these is the most suitable fuse for the espresso machine circuit? So there's quite a lot of thinking to get this 1 mark here. I've been given a voltage and a power, and I care about a current. So I'm going to use the equation P equals IV and rearrange so that I equals P over V. Now 3.5 kilowatts is 3.5 times 10 to the 3 divided by 440, and the current comes out as 8 amps, which isn't an option. I need to go for the one above that, so I'm going to go for 10 amps. Then, before the espresso machine can be used, its heater must raise the temperature of some cold water. The specific heat capacity of water is 4,200 joules per kilogram per Kelvin. Show that it takes the heater about 90 seconds to raise the temperature of 1 kilogram of water from 18 to 95 degrees C, using an equation from the formula sheet. Firstly, in a show that question, you have to basically ignore that you've been told 90 seconds, pretend it says, what is the time, and then show that it's close to it. So you can't use that 90 seconds in your question. So using an equation from the formula sheet, here's the formula sheet, we care about the specific heat capacity question equation, which is this one here. So we've got delta Q, which is energy in, equals M, mass, times C, specific heat capacity, delta theta, which is the change in temperature. And I'm looking for the time it takes to work this out. Now, there's no time in here, but thinking back to the last question, I was given the last part of the question, I was given a power of 3.5 kilowatts, and I also know that power equals energy over time. Now, annoyingly, this is the symbol Q, which is also energy. This is the energy in or out. So if I can work this out, I can work out the time. So delta Q equals the mass, which is, I'm told, 1 kilogram, times C, which is 4,200, times the change in temperature. So it's 95 minus 18 degrees. Because these are both in degrees Celsius, I can use them in degrees Celsius. If you are looking at this later on, you might come across Kelvin. Sometimes you have to use Kelvin temperature, but here we can use either. So I put those numbers in, and I get the change in energy, or the energy in, is 323,400 joules. Now I know that power equals energy over time, which means that time equals energy over power, which is 323,400 divided by 3.5 kilowatts, so times 10 to the 3, and the time comes out as 92.4 seconds, and that is approximately 90 seconds, so I can be happy and know that I've done that correctly. So show that questions are nice, because if you get the answer right, you know you've got it right. Right, part B. The espresso machine has a steam pipe that can be used to heat milk in a jug, as shown in figure 28. Steam from the pipe enters the milk where the steam condenses to water. The steam and the hot water heat the milk. Describe in terms of energy how the arrangement and movement of particles in the steam changes as the steam enters the milk, condenses and cools. So when the steam goes from being a gas to a liquid and then a colder liquid, so the particles move closer together and slow down. Now it's asked you to work it out in terms of energy. So the fact that they slow down means they decrease, so decreasing their kinetic energy. And because they've slowed down, and also because they're getting closer together, it also decreases their internal energy. So there are your 2 marks there. And so now we come on to basically the last 2 parts of this question, and this is the really, really hard question here, okay? So if you feel a bit lost, don't panic, you're normal. So we've got a specific heat capacity of milk. I'm going to write this down as C M. 3,840 joules per kilogram per Kelvin, which is slightly less than the specific heat capacity C, W of water. The specific latent heat of the condensation of steam is 2,260 kilojoules. Don't miss that out. And latent heat, if we look at the equations now conveniently next to me, is L. So I'm going to call this L of steam. The temperature of the steam is 100 degrees Celsius. The mass of the steam is 25 grams. And the temperature of the milk rises from 5 to 65 degrees. So if you've got some cold milk and some hot steam at 100 degrees Celsius, the milk will get hotter, the steam will get colder, and it will get colder to the point where it's the same temperature as the milk. So the steam is going to go from 100 degrees Celsius down to 65 degrees Celsius because they'll meet in the middle. They'll basically do this. Now, steam can't just go down to 65 degrees Celsius because steam has to become water before it can then reduce down to that temperature. So there's two parts to this question. The energy to heat the milk is going to equal the energy to condense the steam from steam to water plus the energy to cool the water from 100 degrees to 65 degrees. So there's three. It's a really, really hard question. So the energy to heat the milk, because milk is a liquid and it stays a liquid, we're going to use the specific heat capacity formula. So M of milk times C of milk times the change in temperature of the milk equals the energy to condense the steam. Now that's the specific latent heat. So it's the mass of the steam times the specific latent heat of the steam plus the energy to cool that steam. Now it's gone to water at 100 degrees Celsius down to 65. So that's the mass of the steam, which is the same as the mass of the water. 25 grams of steam is 25 grams of water, times the specific heat capacity of steam, which is the same as the specific heat capacity of water, times the change in temperature of the water. And we are looking for the mass of milk. So this is what we want to find. So the mass of milk times C, which is 4,200. No, that's not, sorry, that's the mass, that's the water. 3,840 times the change in temperature for the milk. The milk goes from 5 to 65. That's the change in temperature. Equals the mass of the steam, which is 25 grams. I'm going to remember that I'm doing this all in grams. Times the specific latent heat, which is 2260 kilojoules. So 2260 times 10 to the 3. Plus the mass of the steam, which is the mass of the water, which is 25, times the specific heat capacity of water, which is 4,200, times the change in temperature of the water. The water goes from being boiling, 100, down to 65. So I've got all my numbers in, and I need to be super careful with the calculator, because when I did this before, I got the wrong answer. So 3,840 times 60, as this is 230,400 times the mass of the milk. 25 times 2260 times 10 to the 3 comes out as 565,000,000 plus 25 times 4,200 times 35 as this, 35 as this is 3675000. Add these two up and we get 60175,000 and divide it by 230,400 to get the mass of the milk, and it comes out as 261. Now be careful, if you write 261 kilograms, that's a bit ridiculous. I've kept all my masses in grams because there's a mass in each side, in each term, so that's okay. So I just need to now remember to then convert that into kilograms, so 0.26. That is a horrendous question. I have never seen it come up again because my year 13s would struggle with that, some of them. So finally, give two reasons why the actual mass of steam needed to heat the milk is greater than 25 grams. And any question in specific heat capacity of why is it bigger is always because of energy losses. So some energy heats the jug or surroundings, not the milk. So we'll need to replace that. and also some steam will escape. You've probably seen it in a coffee place. The steam comes out, some still will escape, so needs to be replaced. Which isn't a horrible end to quite a difficult question. So there we are, quite a slog, that paper 2. Hopefully it was doable. This final question, the final 2 questions are very hard, so if you found them tricky, you are completely normal. Well done.